So the second presentation is process glass aggregate, glass cullet, quantifying deleterious materials content, allowable limits and economic analysis. And this is given by Dr. Mandar Dewoolkar. He's the interim dean, College of Engineering and Mathematical Sciences, and professor of civil and environmental engineering at the University of Vermont. Mandar has 30 years of experience as a researcher, consultant, and educator. He's currently interim dean of the College of Engineering and Mathematical Science at UVM and professor of civil and environmental engineering. He's a registered professional engineer and specializes in geotechnical and geo-environment engineering. So welcome, Mandar.
Thank you. Thank you very much, Dale. I appreciate the opportunity to present this work here, which we have been working on for last over 3 years. And of course, a big thank you for TIDC for funding it and US Department of Transportation. So I'm going to talk about essentially crushed recycled glass, which is often referred to as glass cullet or processed glass aggregate. We typically put our bottles once we use in recycling and assume it gets recycled, but actually it's quite difficult to use recycled glass as glass again because it has to be quite clean. So a lot of glass doesn't get recycled as a new glass, and there is a lot of interest in finding use for it. So the title is Quantifying Deleterious Material Content. So the glass, when we recycle it, particularly if it's single source, when you put glass, plastic, paper, everything into one bin, there is a lot of material that gets crushed along with glass, such as paper labels, plastic caps, and things like that. Nowadays, a lot of people shred documents at home, and that gets stuck to bottles, and that also makes it into the mix. So, and there is not a real good way of determining what that deleterious materials content is. One would find literature on showing that crushed recycled glass can be used. Its geotechnical properties are acceptable, but there hasn't been any systematic evaluation of what is the allowable limit on it in terms of meeting engineering properties. And finally, is it economically and environmentally beneficial? So just a quick plug for the University of Vermont. We were founded in 1791 when TIDC was formed. We had a hope that one of the annual conferences would be on our campus in Burlington, Vermont, but we did not get a chance. So I'm showing you some pictures. We have a beautiful campus, and we are in Burlington, Vermont, which is on Lake Champlain. So if you have an excuse, please come and visit us and send your kids to UVM after you consider UMaine. So the benefits of the project. The project came around to us as some local issues in Vermont around recycled glass. So as I mentioned, in Vermont, we are mandated to recycle glass, but it's single source recycling, and glass cannot go into landfill. That's the state law. So Vermont Agency of Transportation actually has a spec that allows glass with a deleterious material up to 1%, and China, like China plates, glasses, cups that make into the mix, up to 5%. But their major problem is how to reliably determine what is the content of those deleterious materials in the crushed glass. And once we started working on the project, the interest in microplastics kept on going. So there was an added interest on determining what is the plastic content in the glass. The second question they had, what is the allowable, what is the maximum we can allow so that they meet the engineering properties requirement. And nationally, if you look at the specs from different states, we were able to find about 22 states. The allowance varies between 0.05% to 10% for deleterious material content, and typically 5% ceramics or China. And the third question is, at least for Vermont, does it make sense economically and environmentally? Unfortunately, right now, quite a bit of recycled glass actually gets shipped out of Vermont, which adds a lot of money to the transportation and emissions. The goals of the projects were to come up with a reliable and operationally simple method so that recycling facilities or the end users could easily determine the deleterious material content in a crushed glass. And then make some recommendations on what could be the maximum allowance for deleterious materials in crushed glass. Vermont was specifically interested in using it as sand borrow, which is essentially good grade, free draining, granular sand gravel type soils that they use, which are naturally available, but their sources are also depleting and it's becoming quite expensive. So could we save that material and use glass instead was the idea. And how do we use these results and take them into practice and in general catalyze the use of glass in Vermont and beyond. So when we started on the project, we had a technical advisory committee. So we had a bunch of people from Agency of Transportation and Natural Resources from Vermont, and also from two recycling facilities. So about 10 people, we met with them quarterly in order to get their feedback. So whatever we were doing was relevant to them. So going to the first question, how do we determine deleterious material content? We thought, how difficult can it be? The current practice is based on visual inspection. So basically you take some material, dry it out, maybe about a couple of pounds, and physically separate everything that looks like it's not glass. So here are 3 samples of PGA, one from Vermont, one from New Hampshire, and one from Massachusetts. And there is a US penny in each picture. So you can tell it's not quite possible, particularly for one from Vermont and one from Massachusetts, to figure out, oh, this looks like peanut butter, let's separate it out, right? Or paper or plastic. Plastic is a little bit easy because it has color usually. So in general, the current visual method that's also mentioned in AASHTO specifications is not reliable and practical, particularly for finer grained PGA. But that's the only method that's available. So our goal was to come up with a different method that works better. So the materials we tested are these, some from Vermont, one from New Hampshire, and one from Massachusetts. And on the right side, the picture is different types of deleterious materials that one can find. And we call these samples RFPGA, RF for recycling facility. So these are real samples. However, we don't know for sure exactly how much deleterious material content is in these materials. So we came up with our own lab manufactured crushed glass. So we use this machine and use clean glass to crush it to create clean glass samples. And its grain size was very similar to the one produced in Vermont by a recycling facility. And then we added paper, different types of papers, plastic, steel, and peanut butter and other food items in order to, so that we know how much deleterious material went into it, and then tried to come up with methods to actually determine it. So we thought, how difficult can it be? But it actually turned out to be quite difficult. We tried many, many different methods. And finally, we figured out that these 3 techniques, using a magnet to separate ferrous materials, combustion to 550 degrees in a combustion oven, and density separation with water by simply floating the material. These 3 things work quite well. So, So whatever PGA sample we would get, you would dry it out to 110 degrees, pass it through this universal sample separator for 3 times, just to make sure it's well mixed, and pick 6 samples from it at 1200 grams each. And then we ran all of our testing on these 6 samples. So the first protocol has 2 parts. One is magnet test and then combustion. So the 1200 grams, you spread it out and then take a magnet over it several times until no more material gets stuck to it. So this removes all ferrous metals. and then put the rest of it in a furnace at 550 degrees and mix it once after 25 minutes. The second protocol took 1200 grams of crushed glass, and added 1500 milliliters of water and stirred it for 2 to 5 minutes pretty vigorously and let the materials float to the top. And you separate those and dry them out. So, and then once that happens, you separate those out in what looks like plastics of different colors. Then you also take the material that actually, okay, it has a, okay. So the things that didn't float, you dry it out and then visually separate all the things that look like plastic. And then you use this technique called FTIR, where you put one piece of what looks like plastic at a time under it. And you can run your analysis, and it tells you can use some criteria to figure out if it's plastic or not, and if it's plastic, what kind of plastic it is. So 1200 gram sample, depending on how much plastic there is, it could take a couple of days to run this detailed analysis. But we have grad students with a lot of patience. Neha and Fiona, who were on the first slide, were very patient, and they did this. So I can't show all the results, but I picked a few results. So this is a lab-based sample that we made that is 98% glass, pure glass, clean glass. And then we added 2% deleterious materials, 2 types of plastics, 2 types of paper, and some peanut butter to it, which sticks pretty well. And here are some sample results. So the first one, it has 6 samples, right? So please look at the first row of pink numbers. Magnet test gave 0.02% by mass as ferrous metals removed. Whereas since we didn't add any metal, we were expecting 0%, which is the bottommost row. So glass has some impurity there. And then we added 2% other stuff, which was all technically combustible, and about 1.9% instead of 2% was detected through that. So the total deleterious material content came out to be about 1.9%, where we had added 2%. And when we used the second protocol of just floating the material, it was 0.8% plastic. Paper actually sinks once it gets wet. So, and it measured all 0.8. Okay. So the other things we did is we repeated the same test with different types of materials that we made by 3 different operators, and it showed that the results are very operator independent if they follow the protocols. And we also, through statistical analysis, were able to show that using 3 samples is sufficient. One doesn't need to do 6. So just quickly, real materials that we acquired from Vermont facility, New Hampshire facility, and Massachusetts facility. And from Vermont, we got it in different seasons. The numbers for total deleterious material content varied from about 0.5% to 3% by weight. And the float materials for the second protocol was anywhere between 0.1 to 0.8%. So in terms of plastic, how much was it plastic? So after doing this tedious analysis, let's look at the 6 Vermont samples. This is real from recycling facility. When we just floated the material and separated it and actually did the analysis on it, the FTIR analysis, 0.2% of the material floated, but only 0.04% turned out to be real plastic. The rest was other types of materials that was not plastic. And that was true pretty much for all Vermont. Whereas even if we consider everything that floated as plastic, it was very conservative. It was somewhere between 40 to 400% more conservative to assume that it was all plastic. New Hampshire, the numbers were pretty close, whereas Massachusetts, there was actually more plastic in the PGA because some of it did not float. But in general, it looks like it's conservative to assume whatever floated all as plastic if one doesn't want to do all this type of detailed analysis. So I think I already talked about it. So in general, protocol 2 gives a conservative estimate of plastics content. So what we learned that we recommended only protocol 1, which is simple magnet test and combustion test to get a good estimate of overall deleterious material content. And however, it does not capture non-ferrous materials such as aluminum, but based on interviews with recycling facilities, they don't expect much metal in it. And it cannot capture ceramics, which is fine because we did a bunch of testing to show that ceramics don't actually change material properties of or engineering properties of glass. So protocol 2 is only recommended if stakeholders are interested in figuring out the plastic content in glass. And we were able to show that the protocols were reliable and operator dependent. Question, I have no idea how I'm doing on time, but no warning, I'll keep on going. For 5 minutes. So then we did a bunch of testing to figure out what is the hydraulic conductivity, compressibility, and shear strength. I'll just spend a minute on hydraulic conductivity. We also obtained 3 different actual borrow soils used in Vermont. One of it is from New Hampshire quarry. And the permeable hydraulic conductivity results from 3 different soils were here. For borrow 1, it went from 0.05 to 0.055 centimeter per second. So the total range is the blue column. So when we tested the real PGA materials we had, it was all higher than the minimum permeability from real soils. And all the lab concoctions that we made by adding paper, plastic, ceramics, and all those kinds of things also had acceptable permeability. So which this shows. We did large-scale direct shear testing and also found that the friction angles involved of PGA is slightly lower than real borrow soils we tested, but still acceptable, plenty high internal friction angles for it to be used as a material. And so that's what we found out, and similar results on compressibility. So even with 5% deleterious material content, we found that the engineering properties, geotechnical properties were acceptable. And we also did some testing with 20% China ceramics, and even that those properties were acceptable. Finally, is PGA economically and environmentally viable? So we use Vermont as a case study. And I'm going to just talk about economics part of it. So Vermont produces about 21,000 tons of glass. It's only 630,000 people in Vermont. So we out of which 2 big recycling facilities handle about 75% of it. And the rest goes to some other facilities, and about 7,300 tons go to 5 cents per glass things that people turn in. So only the MRF1, which is the recycling facility number 1, processes glass and turns it into crushed glass. They have the equipment for doing it. But combined MRF1 and MRF2, which is almost 14,000 tons, and that's how much sand borrow is used by state DOT alone for their projects. So Vermont actually has less gas that we produce than the overall need in the state for sand borrow. But right now, most of it is either stockpiled or getting shipped out of state. So the second recycling facility actually, okay. Okay, second recycling facility actually sends all their glass outside to South Carolina, which is a lot of transportation cost. It says over there that the facility 1 currently loses $33 per ton of PGA. So we looked into, they earn actually $520,000 in our accepting the glass, but they spend about $455 in processing it, and another $250,000 to ship it out or to stockpile it. So even if they give it away so that's how they lose $33 per ton. So even if they give it away for free, they will save $12 per PGA if it gets used. So, and then, so that economic analysis is quite clear that it's a good thing if we can do it in Vermont, and presumably this could be the case in other states. So we did all sorts of other analysis, but that's where I'm stopping. So sand barrel replacement will reduce cost for managing glass waste, particularly in Vermont. And it could be a new revenue stream for the material recovery facilities who actually handle recycled materials. And once we stop sending it out of state, there are also a lot of environmental benefits. And we will save natural sand and gravel. So final takeaways, as I said, protocol 1 that we developed, which is magnet and combustion, is simple enough and can be operationally adopted. Protocol 2 for plastic, we are recommending only if people are interested in it. Our paper is already published in journal or getting published in Journal of Testing and Evaluation for ASTM. As I said, geotechnical properties are acceptable, and economic analysis also showed benefits. So since the session is about taking TIDC research to the path of deployment, we, with the help of VTrans, we met with the AASHTO 1A committee and presented our results. So they are considering replacing the visual classification method with these protocols right now. Both VTrans and Agency of Natural Resources of Vermont collaboratively considering increasing the limit of PGA from 1% to a little higher. And hopefully that will break the barrier and people will start using it once VTrans start using it in Vermont. Finally, there are a lot of people to thank, but I do want to once again thank TIDC for giving us this opportunity. At Vermont, we had about 12 projects that we did. They had various levels of deployment. Professor Houston, who is sitting there, he is working on a couple of concrete projects that we also did with technical advisory committees where the research will get used in practice. So, and finally to all of you for being patient, and I probably overextended my welcome, but thank you.